So the work done gives change of kinetic energy. Now a football, when you take a football, there's no kinetic energy with the football, but when you do work on the ball, how do you do work on the ball? Push it with a force and displace it through a displacement. Now if you do that much of work, you're going to give it kinetic energy so that it can actually move out. So any object, for that matter, if it is able to move faster and faster, there must be some work done. Okay, I don't know if I mentioned this to you. What is the work done by the centripetal force? How much work is done by the centripetal force? Zero. Why? Because centripetal force is perpendicular to the path, always. That is the reason why, in spite of the centripetal force acting on the moon in the form of gravitational force, the moon is not speeding up. So because there's no work done. On the moon or on any satellite, the gravitational force which provides the centripetal force does no work. You get it? The reason why it is not doing work is because it's perpendicular. Yep. So when your car takes a turn at a roundabout, you may be going at a constant speed. There is a force acting on your car in the form of centripetal force, but that force is not supposed to make your speed change. Do you understand? It's not supposed to make your speed change, but makes your direction change. That's what that force is used for. So centripetal force will not do any work on an object because it is at right angles. So we saw the kinetic energy part of it. Expression for kinetic energy is known. Now the other one is GPE, which is gravitational potential energy. And I don't know if I started discussing about gravitational potential energy.
Yeah.
What do you know about gravitational potential energy now? Yes. Yeah. Go ahead.
Work equals the change in gravitational potential energy.
Should be. Yeah. What is gravitational potential? Like how much potential do I have right now?
It's difficult to figure out. We don't know.
It is difficult to figure out. It's a huge quantity though. I may have a potential energy of like 10 to the power of 9 joules. It's a lot of energy. It is the amount of energy needed to bring me from the center of the earth to here. That's a lot of energy. So that is what I have right now. So absolute values of gravitational potential energy we can calculate, but it is out of the scope of what you need to learn. Okay, we can calculate. There are formulae for it. You can actually find out the potential energy of any object here. But just understand it's a big quantity. Right now we are looking at just change of GPE. So the change of GPE is what we are actually interested in. And what is the change of GPE? Like if you have an object sitting here of mass m, if I want to change its GPE, I need to raise it up to that height. So how much is the minimum force that you need to apply in order to lift it up? What's the minimum force required? mg. The minimum force is just to beat the gravitational force of mg. So the minimum force required is mg, and you're raising it through a height of h, and therefore over here the object has more gravitational potential energy than this level. Okay, it has some gravitational potential energy here, and here also it has more potential energy. And how much more does it have is the force times the displacement. So that's your equation for change in GPE. Mass times gravity times the change in height. Sometimes you can see books writing this part like this, mg delta h. Now if the delta h is positive, that means it's picking up gravitational potential energy. If delta h is negative, that is it's coming down, it's losing the change is negative. Okay? So gravitational potential energy is easy to understand, simple equation. Did we do that before?
Yes.
Yes. Okay. Now the next one is elastic potential energy. So you need to know something about elastic potential energy. before we go into elastic potential energy, we need to know something about elasticity. So let's talk about a spring which can be stretched. So if this is a spring, that is unstretched, this is unstretched. And if you apply a force on the spring, it stretches. If you apply a force, it will definitely stretch. And the amount of stretching is directly proportional to the force that you apply. You apply more and more force, it stretches more and more. So F is proportional to X. F is proportional to X. That's if you're looking at this force. Now if you're trying to look at the force that is coming in from inside, that is the force that is setting up inside the spring, trying to restore it back to its original position, that will be an opposite force, right? So this is the force that you are applying, and that will be an opposite force that is set up inside the spring. And this thing is actually called Hooke's law. Hooke's law. Force is proportional to the extension. Of course, this is not true for any force. There are limits, right? Like how much is the extension or how much force? There's a limit for it. I can't just go on putting infinite force. Okay, so we have force constant of the spring. So this could be indicating the slinky, and this could be a very tough spring. So when it's a tough spring, you need to exert a lot of force to stretch it even by a little bit. In a car, for example, the amount of compression on a spring, you can expect very tiny bit in spite of a lot of weight put on it, right? So how much it stretches by, so K will be a factor. K is a special constant for a spring. Now your shocks in your car, they're supposed to have a certain K value, okay? Now sometimes what happens is by overusage and all that, the K of one of the springs will be lesser. It can, the spring can get weaker. So once the K value goes down on one spring, that means what? That will stretch a lot more than the other ones. And you can see the consequence when you go over a speed breaker. It's supposed to go together, right? Your car has to go together. The wheels have to go up and down together. And if you find as soon as you go over a speed breaker, the car is kind of doing that, that means the spring constants are not slightly affected. The shocks are getting damaged. So overusage will automatically cause that shake. Every time you go over a speed breaker, one wheel kind of goes more than the other. Yeah?
How are you supposed to 5K if it comes from the F and X, like in the equation?
How do you find K?
Yeah. Is it like given to you? Or?
You can find K for any spring anytime. All you do is take the spring, put a weight on it, find out how much it stretches. You have the weight, you have the extension, you can find it. So to find the force constant of the spring is an easy thing. All you do is, well, in this case, the spring itself is heavy, so even without any weight, it is stretching, right? You normally take a spring, and if you suspend it now, this is an unstretched spring. When you put some weight on it, it will stretch. You know the weight, you know how much is stretched. That should be in newtons, and that should be in meters. Make sure you put all those things right, and then you got the K value, right?
Yes.
Yeah. And there is a force that is actually holding the spring. You see, when you pull it like this, there's a force that is building in the spring upward. There's a force that is carrying it. Like if I'm holding the spring like this, now this spring is suspended by its own weight. So since this is already stretched, there is a force that is trying to restore it back to its original position. It's something interesting, because that force is what is holding the entire spring up. So I'll show you something interesting. Okay.
Go right ahead.
Ready? Are you ready?
Yo, I think he needs to turn the lighting.
At the count of 3, you drop it. Drop it means like just like that. 1. Sometimes you may be given force constants in Newton per centimeter and all that. You need to change it to meters. Okay, Newton per meter. Now, that is F is equal to kx. Now coming to the energy concept. So how much work is done when we stretch the spring like this? Okay, so let's look at the work done part of it. The work done. Work is what? Work is force times displacement. But in this case, is the force the same all the time?
No.
No. So if you have a graph like this with the force fixed and then the displacement is here, how much is the work done? FD. That's FD. But in that case, the force is not a constant because initially there was no force. When you started stretching it, the force started building up, right? So the force is not a constant, it changes like that. So if you're going to stretch it from here to build up the force up to this, by the time you build it up here, it stretches by x. How much is the work done? It's the area under this graph. 1/2 of fx. You get it? Because the amount of work that you do is cumulative. It's actually like if you break it down into multiple rectangles, you can see that it's sum of the area of all these rectangles, because here we are doing more work and here we're doing less work and less and less and less. So initially, to stretch it initially, you don't have to do much work. But as you start pulling it more and more, your force is increasing. So you end up doing more and more work. Do you get it? Well, we can derive it by using calculus as well. But the main idea is clear. The work done in springs is 1/2 Fx. It's not Fx. It is 1/2 of Fx because the force is not a constant. Say it again?
You can call x d though, right?
Yeah, but for extensions, we normally use x. Extensions, x. Or compressions, x. So you'll see that, the terms that are here, you can call it anything you want. Some books call it E for extension. But I think x will be more popular in different books. Alright, so what is this? Work done. Work done on the spring while stretching it is 1/2 of kx, 1/2 of fx. But what is f?
Force.
In terms of k, what is f?
Kx.
So therefore, it is 1/2 kx times x. And that is 1/2 kx squared. This is the work done on the spring, and that is the elastic potential energy stored in the spring. So you now know how much is GPE, mgh, how much is KE, 1/2 mv squared, how much is elastic potential energy, 1/2 kx squared. Any questions so far? So these are the main 3 forms of energy we are going to deal with. K is a force constant.
K F over X.
It is.
And why don't you just referred to it as 1/2. Oh, okay. Never mind.
It'll go back to the same thing
Yeah.
again. Okay.
Yeah, that's much.
All right, now let's see. So concepts wise, you already got the kinetic energy, gravitational potential energy, and elastic. These are the three things that we are going to deal with now. Before we get to the next, like problem solving, because that's the only thing that is left after this is problem solving. So I'll go through some problems here, but before that, let's talk about power. Power. And once you're done with power, you are finished with that exercise. It's only a matter of application after that. Okay? What is power? Power is the rate at which work is done. Power is the rate at which work is done. How quickly the work is done. That is power. The rate at which energy is. So power is work done for time, or energy transferred per time, or energy used per time. It's work over time or energy over time. That is power. Okay. Let me give an example. Imagine I've got 10 bricks over here or 25 bricks over here. Let's say there are 25 bricks over here, and I'm asking a little kid, a 5-year-old, to take those bricks and keep it on the tabletop. So the kid is taking one by one, and then putting it on the table. Somehow, all the 25 bricks are up here. On the other side, there's a bodybuilder, and I'm asking that person, there are 25 bricks there, can you bring it up here and put it here? He just goes one big scoop, and he puts it down there. Now, my question to you, who did more work? They're the same. You always think before you tackle those questions. Both did the same work because the bricks were on the floor. They are now here. The bricks were on the floor. Now it is here. So both of them did exactly the same work because the bricks gained the same amount of energy. Yeah.
Would it matter if one person laid all the bricks out flat and the other person put them
Piled it up? Yeah, of course, that's the difference. That's why I just, bringing it to this level, that's it. If you're stacking it, that's a different thing altogether. That's a big difference. So that's why I said he just grabs it like that and puts it right here. So both did the same work, but who's more powerful? Obviously, So why is he considered more powerful? Because he could finish the task in a shorter amount of time. He did the same amount of work, but he did it in a shorter time. Whereas a kid did the same work, but took a long time. Another example can be like I'm giving a running race to two people who are exactly the same mass, right? Mass-wise, they're exactly the same. And the running race is you got to reach the 20th floor by the stairs. And you're going to climb the stairs and go up to the top. So obviously one of them is going to reach there earlier than the other. They both shifted their masses through the same heights. That means they both gained the same amount of what energy? GPE. Right? Try to get familiar with those usage of GPE, EPE, and all that stuff. So GPE, same energy, but the one who finished it earlier, that means less time taken, is more powerful because he could transfer that energy quicker. Right? So power is the rate at which energy is used or energy is spent. That's basically power. Now, the unit of power is work over time. Work's unit is joule and time is seconds. So joule per second is the unit of power. So whether you're talking about energy over time, still it is joules per second. So any form of energy work or energy, they all have joules. Divide by time gets you power. Now instead of writing joules per second, we write it as watts. W. So W stands for watts, which is joules per second. How many joules in 1 second? And now when you talk about your amplifier in your car and all that, you talk in terms of, oh, mine is a 300 watt, or mine is a 2000 watt. You know, like you talk about watts. What is exactly a watt? How many joules per second? That's what basically it is. So anything related to power, you always measure in watts. So what's the unit of power? No, I was just saying it. What is the unit of power? All right. Yeah.
So on mastering, can we put joule over second or watt? Does it matter?
Yeah, both will be fine. Joules per second or watts, both are fine. Now, what's the power of these light bulbs? What
60
is it?
watts.
Read it. It's already printed on the bulbs. No, you won't go blind. Tube lights, they are not.
32.
32 watts, good. Yeah, he was not blinded. 32 watts for the slim tubes are 32 watts each, especially the 4-foot ones. These are all 4-foot tubes. The thicker tubes are 40 watts.
60 watts.
Yeah, so I don't know.
You need a light for an
Oh well, if you're looking at the long ones, like 8-foot ones, then of course they are more. So they go by the size basically. So the smaller tubes, of course, is less wattage. There are 2-foot tubes will be like 20 watts. Yeah.
So what's the energy transferred in the light though?
Light energy,
Like electricity?
radiant energy. Yeah. That's an electromagnetic wave. That's a totally different thing compared to physical things. Okay, that's a different electromagnetic energy. That's a different one. Right. So this tube, when it is marked 32 watts, it means it is spitting out 32 joules of light and heat. Mostly light. Heat is negligible per second. Whereas if you're looking at a normal incandescent light bulb, you know the incandescent light bulbs? They are hot touch, right? The incandescent light bulbs, if it is marked 100 watts, it is giving out a lot of light, but it is also giving out a big proportion of heat. So it's throwing out heat and light. That's why it's not very efficient, because you are using a light bulb for light. So we don't want the unnecessary heating effect, because that's the unnecessary spending of energy. So when you have your lights in your car, if they are LED lights, now LED lights' main job is to give light, not the heat part of it. So if you touch this tube, it's going to be cold. Slightly warm, but it won't be. I can touch it.
I can go for it.
Yeah.
Touch your eyes with it.
You touch it when you go blind.
It will be.
Just dive on the ground.
It will be just gently warm.
It's like lukewarm.
It's just lukewarm, yeah. But the other incandescent light bulbs, you can't touch them just like that. They are hot. All right. So similarly, any gadget that you see here, they all have some power rating. The television probably is 60 or 80 watts. Computers, they have their own wattages. Anything that we use, now my kettle is 1,000 watts.
Oh, is it?
What?
The kettle. The white thing there.
Tea or coffee with that?
I make anything. It's just hot water. I just pour water in it and then just boil it and use it for any purpose. If I just want only hot water, I can just take hot water. Yeah, that's not a coffee machine. It's just like water. Just boils the water up. All right. So that is 1,000 watts, and that's why it actually like heats up the water in just less than 5 minutes. That thing will begin to boil and to shut off. So that's an electric kettle. Your hot plates at home, those are all like 1,500 watts each. So it's a lot of power, and that's why strong electrical wires are required to connect to your system. Yeah.
Does it turn red for like, is that because of the heat or is that because it's like telling you
It's just a sensor. Which one turns red?
like the
Oh, the surface. Yeah, that's right. It is. You know, when something is hot, it actually starts giving out. It's an electromagnetic wave. When the temperature goes above a certain number, then the heat radiation will come out as light radiation. So you'll start seeing the orange color first, you know, the reddish orange color, and then if it is hotter and hotter, it actually comes out more yellowish. And if it's super hot, it'll actually go to bluish.
What about white?
Yeah, white is a combination of all of it. Now, if it is blue, that is really hot.
Is there anything harder than blue?
Becomes invisible after that. Ultraviolet.
I have gas stove at home.
Yeah, you can have a flame that is actually invisible, but it'll be like really, really hot. Like if you look at a blowtorch and all that, sometimes you will not see any color, but it'll be like really hot.
Like
On the
full
stove?
flames. I've done it before and I couldn't see the flame.
You couldn't see
No.
what?
And the flame, you had to like shine like because we were it was at night so we couldn't see it, but if we shined the light on it we could see it. I don't know, you're in 6th grade, we're not hand sanitizer.
So power is measured in watts, and you know exactly what wattage is. Power is work done over time. Work is force times displacement. So if you're actually trying to drag something, applying a force, it is force times displacement. And if you accomplish that in a certain time t, then power is work done over time. But what is the displacement over time? So therefore we have power is equal to force times velocity. So we have all these equations. So force times velocity, that means if you are actually applying a certain force and if you're moving with a certain velocity, that means you can actually find out how much is the power used. Like for example, your driving force of your car. You know, the driving force by the grip, by friction. If you know what it is, and if you know how fast you're moving, you can find out how much power is actually being put in. Yes.
What is horsepower then?
It's 746 watts. 1 horsepower is 746 watts.
Is that how much a horse would really do?
no.
It's I don't know how it, you know, I think it started off with the suction cups thing, you know, evacuate, you know that, right? 2 cups like that put together and then evacuate the whole thing, make it vacuum inside, and then they used horses to pull them apart.
What?
Yeah.
Literal horsepower.
And they did some bunch of calculations and then they came up with this number, sort of. That's why it's called horsepower.
Because the horse
So a
is
stove is about 2 horsepower.
Yeah, like pulling from both sides. It's a suction cup thing.
The horse is pulling at exactly 746 watts.
I mean, I don't know what they've done to really get to that number,
So it's not the actual.
but it is some kind of a. It started like that. It started like that, but it evolved into a certain unit. It is not. It is not something that we use very commonly. It's not SI unit. This is not an SI unit. That's your SI unit. All right. Now you have done kinetic energy, potential energy, and all those things. Now, next. Yes.
Doesn't technically the sun have its own horsepower?
Sun is what?
Can the sun be measured in horsepower? No.
You can measure anything in horsepower. So all you do is just convert it. Normally, people used to measure, water pumps and motors and all that with horsepower ratings. Like that's a quarter horsepower, that's half horsepower, things like that. But SI unit is still watts. Okay. Terms that you have already gone through. Work. Positive work, negative work. You know what it is, right?
Yes.
Yeah.
Kinetic energy is a consequence of work being done. Or potential energy can be a consequence of work being done. Or elastic potential energy can be a consequence of work being done. Now, Conservation of energy.
Oh, I know this.
Conservation of energy. What it means is this: energy cannot be created nor destroyed. It can only be changed from one form to another. Energy cannot be created nor destroyed. The actual, this is conservation of energy. Energy cannot be created nor destroyed. They just kind of change over from one form to another. And when you talk about one form to the other, like work, kinetic energy, potential energy of all forms, okay, light, sound, everything is included in it. So what kind of energy conservation is taking place in that light bulb? Electrical energy is being used from here to transfer it to light and heat, right? So you can see like what form of energy is getting into what form. A microphone. What form of energy is changed to what form? A microphone.
Electric
Sound.
electricity.
First is what?
Sound.
Sound. You speak into it,
Sound, electric,
sound energy. Converted to
electric.
electrical energy.
How do they work?
You'll learn it next year.
It's an app.
Most of these things, you'll learn it next year. Because a microphone, a loudspeaker, all those things we'll study in detail. So it'll be good. Yes?
So, like, in order for something to lose kinetic energy, it has to be given off in different forms of energy,
Yeah.
right?
Mhm.
So, like, theoretically, if, like, a runner was running in a really hot temperature
Mhm.
and running in a, like, moderate temperature, then they would be faster in moderate temperature.
Like if they trained in
Is that
hot
yeah.
weather and then they ran in normal weather.
They're giving off less heat energy.
Where they're giving off less heat?
Or, I don't know if they're giving off less heat, but, like,
Where? Where are they giving less heat?
moderate.
Yeah.
No, where? In the sense like you said, okay, a cold place and a hot place, right?
Yeah.
Okay, where do you think he can do better according to the concept?
I would assume the colder place.
How?
I don't know, if you were like,
Because in the colder place, you're losing a lot of body heat as well.
If you run in the 90s, it's 8.6 degrees warmer.
Yeah, yeah.
Really?
I mean, if the temperature goes really up to a certain extent, which is exactly a body temperature, that means there's no give and take. And so all of it is basically for you. But that's a very trivial amount of energy. The amount of heat loss and all that is very little energy compared to the mechanical energy that you're putting in. But yes, that concept, it makes sense there. Technically speaking, yes, if you're running in a cold weather, you are actually losing heat energy as well. So therefore, you have to compensate for that. Now, generally, people, in winter, you feel more hungry. Right?
Yeah.
The reason is the same. In winter, you lose more body heat overall. So therefore, you tend to feel more and more hungry. In summer, you won't feel that hunger, but you'll feel thirsty. Because in summer, you are actually sweating it out. Why? Because since it is hot, your body temperature is going beyond its normal requirement. So the body realizes that you're heating up unnecessarily, so it starts making you sweat. It produces sweat, and then after that, the sweat is what is making you cool down and all those things. So you lose water. And therefore, in summer, you will tend to drink more and more water. In winter, you sometimes forget about drinking water. In winter, you tend to just ignore about water completely because you're not losing much water. Instead, you lose energy in the form of heat, and so you feel hungry. So in winter, you're hungry. In summer, you're thirsty. All right? So some people end up putting more weight in winter because the body also kind of starts accumulating energy, considering the fact that, okay, you're losing energy continuously on a daily basis, so therefore let me stock energy here and there. Yes.
Alright, so just theoretically, if you
As I said, energy can be changed from one form to another form. So you can have different forms of energy. So here, let's say, for example, if an object, gravitational potential energy, sometimes you will be told gravitational potential energy is gravitational potential energy, as I said, it's always there, but we can always put some references. We can take the reference as the floor. If you take the reference as the floor, we can consider that the floor is at zero gravitational potential energy. All right? So you can always take reference points anywhere. I can take the tabletop as a reference. If I take the tabletop as a reference, an object on the floor will have what kind of potential energy? Negative. And something here will have positive, because that's your zero level. You get it? That's a zero level. So from here, it'll be positive. From here, it'll be negative downward. So it all depends on the reference points. So normally, we take the floor as our reference levels. So if an object is falling from here downward, what kind of energies does it have here? It has GPE. With reference to here, the GPE is mgh. And if I'm starting from rest, what is the kinetic energy there? 0. And when it comes down, what form of energy is it losing? GPE. And what is it gaining? Kinetic. So when it reaches here, the GPE relatively is
0.
And kinetic energy will be something.
3,000.
Is this all under conservation of energy?
Conservation of energy is what I said, simple. Energy is not created, not destroyed, it's just changed over. Now, I'm showing some illustrations of this changeover. So what is happening over here is the total energy is supposed to stay constant. So the sum of this and that should be equal to sum of this and this. You understand? That is a conservation. And since kinetic energy is 0 there and potential is 0 here, essentially it means whatever GPE is lost is gained as kinetic energy. So GPE lost is equal to gain kinetic energy gain.
So at the bottom, the kinetic energy.
Half mv squared. So if I equate it, now what is what is potential energy loss? mgh. That's a loss. And what's the gain? Right? Now knock the mass off. What does it also tell you? You drop any object, when it reaches here, it has to have the same velocity. You drop any object, whether it's a marker or the book, it's supposed to reach there with the same velocity. So that's what you can see, mass getting cancelled out. Yes, in vacuum. Right? So what is v square? V square is 2gh. And so what is v? Square root of 2gh. So if you know the height from where it's being dropped, you can find out how fast it's going.
Is it CG?
Now, in previous chapters, in chapter 3, you were doing the same question by using equations of motion. If I asked you the same question in chapter 3, I'm dropping this object through this height. What is the speed over here?
Yeah.
So what you'll do then is, by using equations of motion, what is the initial velocity?
0.
Final velocities, what do you want to find out? What is the acceleration? Or negative g. And height dropped, negative. So how do you use the equations of motion? Vf square is equal to Vi square plus
2.
and Vf square, Vi square is 0, so 2 times negative g times negative height. So Vf square is equal to 2gh. That's exactly what it is. So you can actually see that some problems that you actually worked out earlier, you could do by energy conservation method. You see it? You could just use energy conservation method, much easier, much faster. The energy conservation method is much faster sometimes when you look at this. I'll show you more examples of this. So you can find out how fast something is landing just using energy conservation. Let's look at this one. That's a frictionless inclined plane. And the angle of the incline is 60 degrees. It's a frictionless inclined plane. And if I had asked you this question earlier, saying this is a 10-meter long inclined plane, and I release an object here of mass m, as soon as I release it there, because it's frictionless, it starts coming down. When it reaches here, how fast is it moving? So what you would have done with your previous knowledge, what would you have done? You would have resolved the forces, right?
Yeah.
What's the force downward?
mg sine.
Mg sine theta. That's right. So you'll find mg sine theta as a force
Yeah.
that's pulling it down.
Yeah.
And then you will use equations of motion because you know the acceleration down this way. If mg sine theta is a force, what's the acceleration? G sine theta, right? So you have the acceleration, you have the initial velocity 0, you have the displacement 10 meters, and you can find out how fast it's reaching here. You get it? Just by using equations of motion and Newton's laws. But now we are solving it a different way now. The same thing can be solved by using energy conservation. How do you solve this? By using energy conservation. Think about this. What kind of energy does it have here? And what kind of energy does it have here? So GP lost is equal to kinetic energy gain. So how much is GP lost? Mg times h is kinetic energy half mv square. M cancels off as usual. And what is the height lost? It is not 10. What is the height? The vertical height. So this is one level. This is the other level. So the height is here. The height dropped. So how much is this? 10? 10 sine 60. How much is 10 sine 60? So you have 8.66 meters here. And so we use 9.8 times 8.66 is equal to half v square. So you can find the v. You see, that's by using energy conservation method. See, much easier. This is much easier to use this one than by using Newton's laws and equations of motion put together. Now let's bring in friction. If you bring in friction, how is the problem going to be different? Alright, so why don't you find out the answer for this? Tell me the answer for this. Tell me the answer for this.
I got you.
Give me the answer for this. 9.8 times 8.66 times half v squared. So what is v?
13.03.
So it is going to reach the bottom with a speed of 13 meters per second, right? So if I release this on the inclined plane, if I release it from here, 10 meters down, by the time it goes there, it should have 13 meters per second.
That's no matter the mass, so any mass will have the same.
Yeah, any mass should be the same.
That's,
Yeah.
yeah, but friction.
Yeah. Now, coming to reality.
Oh,
Coming to reality. So what you're expecting to get is what speed?
13.
Instead, if you see that this thing is coming down with 5 meters per second,
Uh-oh.
how much is the frictional force?
No. That's not even 8 meters.
So now I'm saying it's coming down at 5 meters per second. Not 13 meters per second, but 5 meters per second. So now work it out once again. What is the GPE here? Calculate the GPE, exact GPE. mgh. How much is GPE? Oh, well, in this case, I need to give you the mass because friction and all that depends on the normal reaction and it depends on the mass. Yeah, so let me say the mass is say 10 kilograms. So it's a 10 kilogram mass. So it's 10 times 9.8 times the height 8.66. So how much is the potential energy on the top?
Wait, it's 10 kilograms?
I gave you 10 kilograms now, yes.
848.68.
848.68.
68.
Now find the kinetic energy over here. Half mv squared. Half times 10 times 5 squared.
Oh, you have to do. Are we not doing the friction?
You're doing
wait,
It's 125.
125 joules. You see, according to energy conservation, the total energy over here and the total energy over here should have been the same, correct? But what you see now is it had 848 or 849 joules on the top, but when it came here, it only has 125 joules. There's a problem with the counting. There is a loss. What happened? Friction was doing what kind of work? It was stealing the energy. It was doing negative work. So friction is obviously not going to speed it up. So friction is backward. How much is friction? So what do you do? So how much is the difference between the two energies? Find the loss.
723.
Loss of energy is 723 joules, right? 724 joules. That's a loss of energy. And the loss of energy is because of work done by, and that is 724 should be equal to this friction. And what's the displacement?
10 meters.
10 meters. So through all the 10 meters, that friction was doing negative work.
72.
So the friction is equal to 72.4 newtons. So we discovered the frictional force acting on it. Will that help you to find the coefficient of kinetic friction?
Yeah.
Yes. Because the coefficient of kinetic friction
Mu.
so we know the frictional force is 72.4. And you know how much is the normal force there?
Mg cosine.
Mg cosine theta. So that will tell you the normal reaction there. So you can actually find the friction. Go ahead and find it. 72.4 is equal to mu k times mg cosine theta. So 72.4 is equal to mu k times 98 times cosine, so 49. So what is mu k? That's a lot of friction. That's a lot.
Wait, how much is it? 49.
Wait. MG cosine.
Yeah.
Oh, not 40.
It's 98.
Yeah, 49.
49.
Yeah.
Half 98.
Oh, half of it?
Yeah.
Yep.
Yeah, then you just.
And then you divide it, so you'll get you that will get you the
1.4%.
1 point something. So the coefficient of kinetic friction as it was dragging there is that much. That's a strong coefficient.
Strong hill.
So expecting something to come down only at 5 meters per second is not easy. The floor must be really frictional to get there.
Unsaid.
Like floor rubber.
Yeah, how many? Yeah, something like that.
So
Yes.
Yeah, they're close. They're close.